problem showing you about what happens when a charged particle moves through a uniform magnetic field. So to begin with, let's talk a little bit about current and how we're defining it. Physics is about the study of matter, energy, motion, and force, and that energy is what's important here. So know that particles generally flow from high energy to lower energy. That's how our energy flow goes. So in a battery, for example, we talk about the potential. We're talking about energy flowing from the positive terminal to the negative terminal. And that's because current are these charge carriers that deliver energy to the device. So these charge carriers delivering the energy travel from high potential to low potential. So current is used to represent that flow of energy that we're talking about. In other words, the flow of the charge carriers to deliver the energy. Therefore, and this is important, current is represented by the movement of positive charges because our charges go from high potential to low potential, or from the positive terminal to negative terminal, and only positive charges can do that. So if you're looking at current as being the flow of negative charges and you're going to use a left-hand rule, then this video may not help you because it's all about the flow of energy from high potential to low potential, and that's a flow of positive charge to represent the current. So here's what we're going to do. Let's talk about what happens to this particle as it enters a magnetic field. So the X's represent the magnetic field going into the paper, dots represent stuff coming out of the paper, and you can see how it's curving. So it's curving because there's a force that's acting perpendicular to the field, and that's that Lorentz force that we figured out with the right-hand rule. So see the arrow coming out? It's the radius of the circle, and the thumb's the direction of the motion, and the force is always perpendicular, and the fingers are matching up with the field. So let's look at this a little bit. It's circular motion, therefore the centripetal force is equal to the Lorentz force due to the B field. So I know that MAC, that is the mass times centripetal acceleration, is equal to QVB sine theta, where theta is the angle between the velocity vector and the B field. So in this case they're perpendicular, so that makes sine 90 degrees equal to 1. That's going to go away. And for the centripetal acceleration, I'm going to replace the AC with the form of the V squared over R. So AC is equal to V squared over R. Now V squared over R is equal to QVB, and I'm going to define this in terms of the radius of that curve that I just saw. So the radius is equal to mv divided by qb. In other words, it's the momentum divided by qb. So that's what's going on here. Momentum divided by qb determines the radius. And all the particles with their speeds and masses can have different radii. So to kind of sum it all up, it's all about the open right-hand rule. So remember the right-hand rule, your thumb is the current or the flow of positive charges, your fingers are the field and they seek the south, and then the palm is the push. In other words, it's the force that acts on the charge carriers. So here I have this particle, and if I look at it, according to my description, it's going to be curved upwards in a circular path, and I know it's curved upwards because when I apply the right-hand rule, I can see that my fingers are going into the paper, into the field, the thumb's the direction of the charge, and it keeps turning, and that's true because the velocity and the force are perpendicular to each other, and that's our definition for causing circular motion. So I know I'm going to have a mass for the particle, I'll be given its velocity and the charge of the particle, and I'll know the B field strength. And if I know those things, I can figure out the radius of curvature for the circle that it's creating.